Namaste. Welcome to the lecture series on the subject Basic Thermodynamics, Module 3, Part 2 Entropy, Lecture number 10. Myself, Dr. nsatheeshkumar, Associate Professor of Mechanical Engineering, Canara Engineering College, Bantwal. The contents for this topic are: you have to prove entropy a thermodynamic property. Then you have to find out entropy change in irreversible process. Then you have to study the application of entropy principle. So now you have to prove entropy a thermodynamic property. As all of you know, if a quantity has to be called as property, the change in value of that quantity between two states for different paths has to be same. Because if the state changes from 1 to 2 and if the state changes along two different paths, for both the path traversed, the change in value of that quantity, if it is same, it is called as a property. In the sense, the quantity has to be a point function, not a path function. So statement says that the integral of del q by t for any reversible process is the suffix r written here. So indicating that it is a reversible process between fixed end states is independent of path. So that's what I told you now. So here the change, okay, between the two states should be independent of the path. Means whatever the path you follow, the change has to be same. So in symbols you can write that, suppose if you have two arbitrary paths A and B between two states 1 and 2, if you move along 1A to 2, or if you move along 1B to 2, like this here you can see. So from 1 you can move along 1A and come to 2. Also you can move along 1B and can come to 2. So there are two paths directed from state 1 to state 2. So end point and the initial states are same. That means initial state and the final states are same, but they are going through two different paths, and you have to prove that for these two paths the ratio of del q by t, since both are reversible, so suffix reversible I would repeat it again and again, okay. So del q by t for this path 1b2 and del qr by t for path 1a2, so both are the same or equal. Now to prove this, so we have considered this reversible cycle 1a2 c1, means now I am taking one more path through which I am completing the cycle. So I can come from 1 to 2 along path A and go back to 1 along path C. That means in the cycle, in short form if I write, it is 1a2, that is the forward path, and return path is 2c1. So cycle I can write it as 1a2 c1. Now for this system I can write as, for this is AC, instead of writing 1a2 c1 full cycle name, you can just write the two path names, that is A and C. A is the forward path and C is the reverse path. For this path del q by t is equal to del q by t for path 1a2 and del q by t for path 2c1, because 1a2 is the forward path, you can see here in the diagram, and 2c1 is the reverse path. So it is summation of the ratio of del q by t for the two paths, and this quantity is equal to 0. The sum is equal to 0 because it is a for cycle, okay, and also it is for the reversible cycle, okay. So this is already proved. For reversible cycle del q by t is equal to 0 in previous one of the previous lectures. Okay, similarly you can come from 1 to 2 along the path B, like this. I am not drawing exactly above the 1b1, just below that, and I can go back to 1 along the path 2c, okay. So cycle is completed 1b to c1. So earlier 1a to c1, now 1b to c1. So here for this path, so now again for a cycle BC, I am writing only two letters of this full cycle name BC. So again 1b to for the path 1b2 the ratio del qr by t, and for the path 2c1 the ratio del q by t or del qr by t. So again it is equal to 0 because this is also a reversible cycle. So previously I named that equation as 1, that is for 1a2c1, and for this path or cycle I am naming it as equation 2. Okay. Now equation 1 minus 2. So 1 minus 2 means don't consider this part. So you will consider only this part of the two equations. So there what you have in the first equation in the previous slide, 1c2. So this is 1b2 here, and previous one equation number 1 you have 1a2, and here both the terms are same. The second term is same in both the equations, and you are subtracting, so this term gets cancelled from both the equations. So let me write that. So this is the first term of the equation 1, second term of the equation 1 minus equation 2 first term and equation 2 second term. Now these two terms are same, so it gets cancelled. So this is minus, so you can take it to the other side. So it becomes del qr by t for path 1a2 is equal to del qr by t for the path 1b2. So now you proved that to the two forward paths, because you have to prove it for two identical directions, both in the forward direction. Okay. So for both the paths, so the ratio of del q by t is same. That means they are independent of the path. Okay. So that is the explanation for the path A and B. So integral of del qr by t has the same value for any reversible path between 1 and 2. Hence from the definition of entropy we may write S2 minus S1 has the same value of for any reversible path between 1 and 2. So hence you can conclude that entropy is a property. So this is how you have to prove that entropy is a property. Okay. Now let us calculate or find out how to find the entropy change in irreversible process. So for a process that occurs irreversibly, the change in entropy is greater than the heat change divided by the absolute temperature for that process. For any irreversible process, okay, the change in entropy, that is ds, for that irreversible process is greater than the ratio of the heat transfer to the absolute temperature at which the heat transfer is taking place. So ds is greater than del q by t. So now let us prove this. So proof. So consider an arbitrary irreversible cycle 1a to b1. You can see here 1, this is path A, it is written here. This is path B. So 1a2 is the forward path, 2b1 is the reverse path, cycle is 1a to b1. The path 1a2 is traversed irreversibly. Here 1a2 is a irreversible process, whereas 2b1 is a reversible process. That you have to understand. So you have to take one of the paths. So that is what is shown by the dotted curve, whereas the reversible path is shown by the continuous curve. Okay. Now from the Clausius inequality we have cyclic integral of del q by t is less than 0 for irreversible cycle. That we proved in one of the previous lectures, and cyclic integral of del q by t is equal to 0 for the cycle which is reversible. So these two considerations, conditions, we can take it as equation number 1. Okay. Now since the entropy change, entropy is a thermodynamic property, we can write the entropy change for the cycle is nothing but entropy change for the path 1a2 and entropy change for the path 2b1. You see, entropy change for the entire cycle is nothing but the entropy change during the path 1a2. Now here ds suffix is written as I because for irreversible path, and here it is written R for reversible path. Now this you can give it as equation number 2. Now for reversible process, so all of you know that the ds value, that is the entropy change for the reversible path 2b1, is always equal to ratio of heat transfer by temperature. So just that is now we proved. Okay. So ds for the reversible path is equal to ratio of heat transfer to the absolute temperature for that path. So substituting this, you see, for dsr for path 2b1, here is in the equation 2. That means you have to substitute this one in the equation 2. So you will get this term as it is, first term. So in place of the second term here, you have to write this quantity. That is 2b12 del qr by t is equal to 0. So in place of this, you have to substitute. I hope it is simple, you can understand. You have to substitute that. So now using equation 1, so equation 1, just you recall, del q by t is less than 0 for irreversible cycle and equal to 0 for the reversible cycle. Okay. So cyclic integral of del q by t for the cycle is nothing but del q by t for path 1a2, which is reversible cycle, plus del q by t for the path 2b1, which is reversible. Since one of the process is irreversible, so this quantity is less than 0. So that is what I told you. The del q by t value is less than 0 for the irreversible process or the cycle. Suppose if we take cyclic integral, then it is for the cycle, so it is less than 0. Okay. Now subtract equation 5 from 4. Now this is very interesting. You have to subtract equation 5 from 4. So 4 first term is 1a2 dsi. So that is written as such here. And here the second term is 2b1 del qr by t. Here that is the second term. Since you are subtracting, this becomes minus. So this term and this term gets cancelled. So one more term is remaining in the second equation, that is equation 5 is 1a2 del q by t. Now this becomes minus here. Now this minus, actually I should write along with this minus this, then I should write the term greater than, but I have taken to the other side, so I can write it as plus. I hope it is very clear. Now one more thing, one very important change you have to note here. So here it is equal to sign, equation 4, minus equation 5, which is less than sign. So equal to minus less than becomes greater than. So that is very, very important. So sign becomes greater than now. When you subtract equation with equal to sign, and with this equation with the less than sign, equal to minus less than sign, so it becomes greater than sign. Now let me show you an example. Just take 4 minus 4, just an example to make you understand why it is greater than. So 4 minus 4 is equal to 0. Now I will write minus 6 plus 4. Now what is this minus 6 plus 4? Minus 2. Minus 2 is less than 0. Now I will subtract, this is 1 and this is equation 2. So 1 minus 2. So 1 minus 2 means this becomes plus, because this is minus of minus, this becomes plus. Okay, this 6 becomes plus and this becomes minus. So 4 and this minus 4 gets cancelled. Here equation 1 minus 4 is there, and this I told you it becomes plus because of minus minus. So minus 4 plus 6, so this quantity becomes plus 2. Now plus 2, is it less than 0 or greater than 0? It is greater than 0. So here what you did, you subtracted from a equation where equality sign is there, an equation which is having less than sign, so equal to minus less than sign, so you are getting greater than sign. So that is what is the greater than sign here. All of you should understand this. And this, how did it come into the right hand side? Because it is minus, I should have written it on the left hand side with the minus sign, but I brought it to the other side, we can become plus. So while bringing other side, the sign won't change. So basic mathematical operations, all of you to understand. Now let us continue with the derivation. So for small changes in state, the above expression, so that is written for a particular process. Now you can write it in general form as dsi, that is for irreversible path, is greater than del q by t for irreversible path. That means for an irreversible path, the change in entropy ds is greater than the ratio of the heat transfer during that process divided by the absolute temperature, or ratio of the heat transfer during that process to the absolute temperature. So this is very important equation for an irreversible process. So here the subscript I represents the irreversible process. So the equation 7 states that in an irreversible process the change in entropy is greater than the quantity del Q by T. So the entropy change is more than the quantity del Q by T. So that is what you have to understand from this expression, right? So now combining, because ds is equal to del Q by T for the reversible process, so combining the two things, you can write dsi is greater than or equal to del Q by T, where equality sign is applicable for reversible process and inequality sign is applicable for irreversible process. Okay. So now let us study the application of the entropy principle. Let us take the case of mixing of two fluids. Now here look into this diagram wherein there are two subsystems, subsystem 1 and subsystem 2, separated by a partition, and entire thing is enclosed in a adiabatic chamber or enclosure. So here subsystem 1 is having mass m1 and the fluid of mass m1. Its specific heat is C1 or Cp1, then temperature T1, whereas subsystem 2 mass is m2, specific heat is Cp2, temperature is T2. So this is what is given here, mass m1, specific heat C1 or Cp1, choice is yours, you can write anything, temperature T1, similarly m2, C2 and T2. Now what you have to do is, you have to remove the partition and the fluids get mixed. So when the fluid gets mixed, so what happens is the mixture attains a equilibrium temperature. So if one fluid is at temperature T1, maybe take it as a high temperature, and T2 is at lower temperature. So when these two fluids are mixed, as all of you know, a hot fluid and a cold fluid, if it is mixed, so the temperature of this mixture, right, it will be between T1 and T2. So Tf, if it is the equilibrium temperature of the mixture of the two subsystems, like you see it is given here. So Tf will be it will be less than T1 and greater than T2. So it means it's less than the hot or high temperature and greater than the lower temperature. Okay. So now energy interaction is exclusively confined between the two fluids, as the system is isolated and moreover it is adiabatic enclosure, so there is no energy flow out of the enclosure or the system. Now you know that one of the fluid gives its heat and it is absorbed by the other fluid. So hot fluid, heat given by the hot fluid is equal to heat gained by the cold fluid. So let us take this one as the hot body. So heat given by this is m1 Cp1 into T1 minus Tf, whereas other body, which is gaining the other fluid rather, which is gaining this heat, is equal to m2 Cp2 into Tf minus T2, because heat quantities are same, because one is giving out its heat, other is absorbing, and finally they are coming to the equilibrium temperature of Tf. Okay. Now from this expression you can simplify, from this equation rather, you can simplify and you can get an expression for Tf as m1 Cp1 T1 plus m2 Cp2 T2 divided by m1 Cp1 plus m2 Cp2. So I request all of you to simplify the above equation and you can get this equation. Just you have to open the bracket and you have to simplify. So now entropy change for the fluid system 1. So what happened to 1? Its temperature has changed from T1 to Tf. So its temperature has decreased. So here delta S1 is nothing but T1 to Tf m1 Cp dt by T. So always you have to write mCp dt by T, you have to integrate, and this is nothing, dt by T is 1 by T, integration of 1 by T is ln T, applied limits upper and lower, ln Tf by T1. So m1 Cp ln Tf by T1. Okay, here as all of you know, Tf is less, T1 is more, so this quantity Tf by T1 is less than 1, so ln of a quantity which is less than 1 is negative, hence this quantity is always negative. That is, entropy change of the system 1 is negative. That means you have to remember like this: the entropy change of a system or subsystem whose temperature is decreasing, or for a substance whose temperature decreases, its entropy change is negative. Suppose if its temperature increases, then its entropy change is positive. Okay. So entropy change for the fluid subsystem 2. So delta S2 is equal to T2 to Tf. So it was also initially at T2, now it is at Tf. So temperature has increased from T2 to Tf. Formula same, M2 Cp dt by T. So M2 Cp ln Tf by T2. Now Tf is higher than T2. So this quantity ratio Tf by T2 is greater than 1. So this quantity is always positive. So this entropy quantity is always positive. So one of the substances which gains heat, it will be positive. For the substance which loses heat, it will be negative. So increase in entropy of the total mass of water or subsystem system due to mixing is delta S is equal to delta S1 plus delta S2. Okay, so I think it is not water. Okay, you can take it as a mixture. Total mass of the mixture due to mixing is delta S is equal to delta S1 plus delta S2. Now delta S, this quantity, is positive, definite, because the mixing process is irreversible. So this quantity, that means when you mix the two fluids, so the entropy change of the entire process is always positive. One of the subsystems or systems or fluids may have negative change in entropy. One of the systems or subsystems may have the positive change in entropy, but when you add these two quantities, the magnitude of the positive quantity will be more than the negative quantity, so that when you add up, the quantity will be always positive. Okay, so with this I conclude this lecture number 10 of this module 3 part 2 entropy, and will continue with the further topics in the next lecture. Thank you.